smooth moduli surface. Smooth moduli? Bundles of surface.
Okay, let's say bundles of smooth manifolds. Smooth manifold bundles. So, let's start with two definitions. A bundle is in the locally, in the sense of the key property is local triviality. So there's a map that has a total space E and a base space B. And the local triviality is U in class B is open, it's homomorphism, for example. And on overlaps, you have two of these. You have two identifications of the inverse images with F. F is some space. So this kind of diagram identifies the inverse image of each point in U with F. If you have two of those, you can compare them and get a map to the group of homomorphisms F. And when we say that the bundle has structure group G, we mean that there are that it is transition map factors through some subgroup of the homomorphism group. So that's some input. An action of a topological group on F. An action should mean a continuous map to the group of homomorphisms. Topological group of homomorphisms of the fiber. So some of this is properties and some of it is extra data. There should be a collection of these trivializations. If this map is injective, say number 2, it's a property that it factors through. What's your map? And then there should be given some kind of maximum chart or something like that. So this is called a fiber bundle. F. And structure P. So the thing alluded to in my title is a special case where F is a smooth manifold. I'll add some more adjectives. Connected. Closed. Sometimes compact and no boundary. And G is the group of diffeomorphisms. And write this diff of M. Diffeomorphism group. If M is compact, I give this the topology of uniform convergence of the diffeomorphisms themselves and all class of derivatives. That subgroup of the homomorphisms and refinement of the topology. And then a bundle with fiber M and structure group diff of M is what I mean by smooth manifold bundle. So studying bundles. Let me also say a more classical example that I'm going to mention a few times as motivation for something, like questions you can ask here that are sort of easier and much older. In the case where the fiber is Rn and the group is G of n. Alright. Then this notion of bundle with structure group G is precisely just a vector bundle. So that's a useful analog, and I think the more things you know about vector bundle, everything you know about vector bundle, you should ask if something that's an analogous question you can ask and answer in the case of smooth manifold bundles. So it was realized long ago, 50s or something, I learned it from Stanford books on fiber bundles, that is a universal bundles. Let's say principle. It's a bundle where F is G and the action multiplication. There's an action. And the universal bundle should denote EG, BG for group G. It's a principal bundle where the total space is contractible. These were proved to exist by Miller, and it was known, as far as I understand, before that once you have existence, the base space BG is, if it exists, it's unique up to homotopy curves. Equivalence with this property of having contractible total space. So therefore we just call it BG, and any model will be homotopy equivalent to any other model. And to a large extent, any question about bundles can be translated to questions about this space. Suppose B is any space, then it maps EG up to homotopy classes of maps. You should say the complex is safe, maybe a manifold or something. Alright, same thing. I mean, natural bijection with fiber bundles. With structure G and fiber. So the fiber doesn't matter for this classification question. It's also a suitable notion of isomorphism. So that translates any question of, or usually you can translate a question about bundles to a question about the homotopy type of this space G. Homotopy Redic. What's this? So let me be a bit more precise in a second, but to study such things, it's good to have models. Like there's an abstract argument that this kind of thing always exists, but that often doesn't tell you very much. The model in the classical model in this case of vector bundles is the Grassmannian. Finite dimensional Grassmannian of B planes in Rn. So I want to write as, well, the point there is a d-dimensional subspace of Rn. I want to write it as an injective linear map from Rp to Rn divided by So an injective linear map is a d-dimensional subspace with a choice of a basis, and then this is dividing out the basis. So this is the space of all d-dimensional sub-vector spaces. And one model for space BT, in that case, the group is GLD of R, or it turns out you can use the same thing for the orthogonal group. Is the Grassmannian, B planes in R infinity, so the union or direct limit. The finite dimensional Grassmannians. So standard fact. Isomorphism classes of vector bundles are in natural bijection with homotopy classes of maps into an infinite Grassmannian. So, and that's useful for proving many things about characteristic classes of vector bundles, that kind of thing. Find explicit cell compositions, decomposition using this model and many other facts. So, what happens to that picture if you have these non-linear objects? Well, there's a space that's sometimes called non-linear Grassmannian. I like the word moduli space of manifolds. Where instead of this RD, let's take manifold M. Instead of injective linear maps, I take injective smooth maps, also known as embeddings. Instead of GLD, namely linear automorphisms of this object, I take smooth automorphisms. So divide out by the group of morphisms of M. And again, the embedding space has some topology that something like uniform convergence of all partial derivatives. This has the quotient topology. I call this BM. It's hopefully the analog is clear. And why you want to call this a nonlinear Grassmannian, because at least the idea is that a manifold is not a linear object, unlike a vector space. And just like in the vector space case, if you take the union over all n, then you get a model for the base space of the thing that classifies smooth fiber bundles. So if you want to understand something about smooth fiber bundles, it can often be translated to properties of this infinite nonlinear Grassmannian. So Okay, so far the analog is pretty close. Once you start actually asking any questions about the space, it quickly gets a lot harder than in the linear case. So what kind of questions should you ask? So a good question is cohomology. So I'm always not quite sure if you're closer to just. Anyway, let me say a few words. So cohomology in this talk is going to be rational cohomology or real cohomology. If you've seen the round cohomology, that's perfectly fine for everything I say. Let me just say 2 words that show any space. The science a weighted ring. Weighted Q algebra. And if X is homotopic to Y, then you get isomorphic rings. That's also one property is that if I don't have a homotopy equivalent to just a map, then I get a ring map in the other direction. That's the reason we're interested in cohomology in this kind of spaces, because if you have a bundle that corresponds to a map, and if you also have a cohomology class, you can pull it back. An invariant of the bundle. Maybe an even more basic homotopic theoretic invariant is the fundamental group, but that turns out to not be so interesting for this kind of space, because it just gives you the group of components of the group G that you put into the question. But cohomology is often, for a particular G, sort of a somewhat difficult question, but not so difficult that you can never solve it. And also, if you solve it, it tells you a lot about the corresponding bundle theory. There's not sort of a theory that just lets you plug in any group and spit out the cohomology. It's something you usually have to redo every time you have a new kind of bundle theory. You need a new method to calculate the cohomology. So for vector bundles, that's an important and quite old story. Yeah. And it's completely understood. I want to separate 2 steps. The first is defining some classes. The important classes were defined by Pontryagin. Cohomology is something about measures something about the curvature of the connection, but there are other ways to define it. And then, because of the ring structure, if you take the abstract thing, once you have made the definition, you can ask what is the entire ring, and you can give a presentation. In this case, a very simple one. happens is that the Pontryagin classes for the index is 0, 2 batch. And then you get the graded commutative, the free thing on the remaining Pontryagin classes. Okay, so that's a classical result. That's very important for every time you have a vector bundle. So shortly, I will talk about the analog of that question for the nonlinear Riemannian. So, and I want to separate these two steps. The first one is defining some classes, and the second one is sort of to what extent are those classes algebraically independent, and to what extent do they generate this ring. So this is something I've been working on over the past 5 years or so, and it's sort of, well, what I wanted to do is kind of done now. Oh yeah. So this is joined with Oscar Randal-Williams in Cambridge. Three fairly long papers. The archive. The understanding is not as good as in the vector bundle case, but it's still a lot better than what it was before the beginning of this story. So it's in some sense a formula for the M, where M is say a smooth compact manifold. Connected of even dimension. The P is going to be 2 times N. Of even dimension, not 4. 2 is for special, so let me say 6. Under some assumptions, namely M should be simply connected. And also M should be diffeomorphic. It should contain many copies of a special manifold, namely S n cross n. And by copy I mean connected summits. You have 2 manifolds of the same dimension. You can take a chart on each of them, cut out a disk from each chart, get a manifold with boundary. Both boundaries are a sphere, and then you glue together the spheres. Glue it together, or you could glue in a cylinder. This is M. This is N crosses N. Draw in the case where N is 1. Is 1, of course, this 1 is a torus. But then this would be a picture of M. Connected sum is N crosses N. And you could keep going. you do it G times, I'm going to write it like this, M connected some G copies of Sm equals to Sm. And then I want this M to be of that form, which should contain many copies of Sm equals to Sm. So in dimension 2, that's just saying that M should have high genus. Or if it's not orientable, surface classification says that it's the connected sum of many copies of real projection space, but every time you have 2 real projection space, you can replace it with 1 torus. So this G here would be roughly half the number of real projection spaces. And then finally, the formula is for this ring up to, in a range of degrees, that depends on this number G. So if you're particularly interested in H1 or H2 or something, then the requirement is not so used. It should. Well, anyway, that's what we do. So I'm not going to write the formula. The formula, I put it in quotation marks because it's really saying that the cohomology in that range of degrees is isomorphic to the cohomology of some other space, which, if you're not a homotopy theorist, it looks like worse than what you started with, but it's really a formula that can, in practice, often be worked out as some specific graded ring. So I'll spell it out in a case. So that's an important special case. Oh, M could have boundary, by the way. Say that. So could have. Empty. Compactness is important, but it doesn't need to be close. P. And then, then def of M should mean the diffeomorphisms that are the identity near the boundary. Say identity on boundary, but it is slightly, technically slightly better to say near. So this wouldn't make a big difference if I just said on the boundary, but let's say it this way. Then this B construction applied to this topological group is again a classifying space for a kind of bundle, and it's bundles with it's again fiber bundles with fiber M. To say B is a smooth manifold, for example. What kind of bundle theory does this have to do with? This identity near the boundary corresponds to having bundles of smooth manifolds with boundary. All the fibers are diffeomorphic to M. But also all the boundaries that you then have in all fibers glue together to a triple bundle. The boundary of E should be the base cross this fixed boundary. identified kind of smooth and fiber-wise. And then all the fibers are diffeomorphic to M relative to their already identified boundaries. This identifies all the boundaries with P, and relative to that, the fibers should be. Okay. For example, this could be surfaces with one boundary component, and then you have a surface bundle. If you look at all the fibers, that's gives you a surface bundle, and that's the kind of bundle I'm looking at. That would be a trivialized surface bundle. So this, the study of such bundles can by and large be translated to the study of this universal space. And this work covers that generality as well. So I write what this formula spells out to in the case where M is the simplest manifold that contains many copies of Sn crosses N is just, you put it in there yourself. So you could start with, for example, like this, and then some many copies of it. So if N is equal to 1, this is just a surface with one boundary component. And if N is bigger than 1, it's some kind of generalization of that. I wanted to mention also, before going into that, with the interest, so I wanted to talk about something very recent that's not due to myself, but uses this combination in a surprising way, I think. It also has to do with, but it's surprising because it doesn't involve these manifolds at all. So I can mention that in my abstract. Due to Michael Weiss, but it goes back much further. It has to do, or I mean, the question goes back much further. It has to do with the case where, so going back to this general setup of fiber bundles with a certain fiber, you could have fiber Rn, just like vector spaces, but you could have structure group or homomorphisms. Instead of just the linear ones. With D. Or even the orthogonal ones. So if you have this structure group, is really, this notion of bundle is really the same as a vector bundle. And here it's a vector bundle with inner product. If you have structure group all homomorphisms, it's just it's fiber bundles where the fibers are D, but without a vector space structure, and the family kind of varies in a nonlinear way. So this is a very interesting case to ask all the same questions. What is the kind of topological study of this kind of bundle, or what are the algebraic topology properties of this classifying space? For example, what's the cohomology? So to this day, that's not known unless D is very small. This is some graded ring. Remains unknown, but still a lot is also known. So maybe it's a little bit similar to this case, that we know it in a range that depends on D here, but we don't know the full answer. So for the general linear group corresponding to vector bundles, we know the full cohomology group. And we don't need to really say further. In this case, it's a good idea to observe that there's a way to increase this number D. If you have a homeomorphism of Rd, you can cross it with the identity map on R and get a homeomorphism of Rd plus 1. The general linear group that corresponds to block sum of matrices make a matrix 1 bigger this way. And that's a commutative diagram like this. That's a corresponding map of these universal spaces. And even though we don't understand, as I said, to this day we don't understand the rational cohomology of this space, the question becomes a lot easier if you keep iterating this construction. Take the stable cohomology. So we take the union of all these, like the direct limit of all these spaces, called the top. That's the classical name. Direct limit equals infinity. So this has to do with the classification of fiber bundles, which fibers are Euclidean spaces, but only classified up to identifying them if they become isomorphic after crossing all the fibers with R a finite number of times. On this side, the direct limit is called BO. And the question becomes easier, or at least still not easy, but it's a long time ago. That's a complete answer. Due to, I think, Novikov, that this is the induced map in cohomology is an isomorphism. There's also, you could put other coefficients. You could put a finite field or something, and then it's not an isomorphism, but this rational theory does not see the difference between having the vector space structure or not in this limit. So in particular, once you know that, you could say, oh, I have this definition of Pontryagin classes here. This, by the way, is compatible. The PI I have here goes to the PI I have there. So they come from a universal PI in the cohomology of BO. So since this is an isomorphism, that comes from a unique PI in the cohomology of this classifying space for bundles of Euclidean spaces up to crossing with R. So that's what that was. Quite a while ago, 60s, I guess. This fact that this is an isomorphism in rational cohomology is really something that's manifestly about this. We're going to call this stabilization. You have some parameter that's a natural number, you have math that increases it, and you have some difficult question. It could be that it becomes easier if you ask it in the direct limit. So that happened here. This map is not an isomorphism in cohomology, but it is an isomorphism up to degree roughly d plus a constant. But outside, and that's sort of why the question becomes easier. Outside that range, they're very different. So in particular, so we have degree 4i. We have the Pontryagin classes, dI, dBGL, dR. So the stable case, the Pontryagin classes are sort of very non-zero. I mean, they're much more than non-zero, they're even algebraically independent in the ring structure. And this was an isomorphism, so that's also true here. Repeating case. But what about in the finite dimensional bundles of fine, oops, this was all 4i. This thing was non-zero. This thing here is 0 if I is too big. So if I is bigger than d over 2. Take a big Pontryagin class with a small dimensional vector bundle, it vanishes. So Michael Weiss has been working on this question. Does that happen for if you don't have the you have these perfectly well-defined classes because they come from here. Characteristic classes of fiber bundles with fiber RD, and if you also have this fiber-wise linear structure, then they vanish when I is big. But do they also vanish if you don't have the fiber-wise linear structure? So Weiss's theorem is that they don't. I'm also going to write it's on the archive, but you're not going to find it if you. It's very weird. That is Dahlian notes on Pontryagin classes.
I didn't hear what you said.
Well, Dahlian notes.
Dahlian?
Yeah, so someone thought that this was reference to Salvador Dali because it was so weird. But really it's because it's a reference to the city Dalian in China. Anyway. So his theorem is that usually the Pontryagin classes are not zero. All right. claims a little bit less than usual. He claims for in a certain range of degrees that are bigger than where they vanish for linear bundles, but up to roughly. This is the range where you might expect them to vanish, but he proved that they're non-vanishing up to at least 5/4 times that number. My understanding is that, well, I won't have too much time to, no time to talk about the methods, but the methods really is a new method. New approach. Homology of this space. And I think what people now know by the same method, it's fair to say that usually they're non-zero, even when I compared to D. Yes. So I was very fascinated by this, well, I heard about it because it used something that doesn't sound like something that's purely about smooth manifolds, and also about very specific manifolds. Maybe I should say D should probably also be even, to be honest. It uses this thing that I have been working on with Randal-Williams. I have no idea that it had anything to do with this question of the homomorphism group of Euclidean space. It uses cohomology of this classifying space for Stewart bundles, the one that had the model with this, what I call the nonlinear cross manual. For a very particular manifold, namely the one I wrote there. So I'm going to give it a name, W subscript G, 1 superscript 2n. So it's like a genus G surface with one boundary component. So that's what it actually is if n is 1. So in that case, so the special case in what Oscar and I have worked on, this is sort of one of the earlier ones. This formula works much more generally, but this case is quite important also, well, for this question. So, well, sorry, maybe you should back up 1 second. There's a construction due to Miller, Morita, and Mumford. Just like for vector bundles, it's useful to separate the question of defining classes from calculating what the entire ring is. You often need to have the classes and be able to talk about them before you try to write the answer. So Miller, Morita, and Mumford define some classes that are often called Kappa classes. Homology of fine print, I should restrict to the M should be oriented, and I should consider only the diffeomorphism, the orientation preserving diffeomorphism. Next question. That's also matter if you have any non-empty boundary. There's no way to flip the orientation, but if you want closed manifolds, then you should say that. So they define some classes there. We're equivalent to some characteristic classes of manifold bundles. In terms of characteristic classes of vector bundles. So restricting to orientation preserving diffeomorphisms correspond to restricting to orientation preserving linear maps. I'm going to change to the SO. Say this is two-dimensional. So that's also an old story. The characteristic classes of oriented even-dimensional vector bundles. There's one extra class, namely the Euler class. And those classes are algebraically independent. Pm is E squared and Pi is 0 when I is. So that can be, well, we don't run out of time. Let me just say that it's not difficult to explain the construction, but if I have time, I can just say it. If you have a class here of degree, say 2i plus 2n, there you can turn a characteristic, or their method turn a characteristic class of vector bundles into a characteristic class of manifold bundles of degree 2 smaller than the one we started with. So every time, whenever, for example, you have P1 to the A1, Pn minus 1 to the A minus 1, An, where the AIs are natural numbers, and suppose that the degree of C should be at least 2n. So 2n plus 2i. You get a characteristic class of oriented manifold bundles.
What's the map?
Sorry?
What's the map from these Miller-Murray-Mumford classes to ordinary characteristic classes of vector bundles?
So the map goes the other way. So if you have a characteristic class of vector bundles, you get one for manifold bundles. Maybe let's say it without writing it. It's because the fibers are oriented and closed. There's a fiber-wise integration map that goes from cohomology of the total space to cohomology of the base. That decreases degree by the dimension of the fiber. And then apply this class to the fiber-wise tangent bundle and fiber integrate that. That's the definition of this thing. Fiber. Right, so we get all these classes, and what in this special case, what Oscar and I prove? When 2n is at least 6. Actually, I should have said that. When n is 1, this was not earlier, of Madsen and Weiss. Like 2002 or something. And what Oscar and I set out to do was to generalize their theorem for surface bundles to bundles of manifolds of higher dimension. And we sort of accomplished that under the, but only in even dimension and not 4 and only simply connected. In this particular case, the answer is that now we've defined these classes. They are again algebraically independent, and if you're a little bit careful about which one you take, they also generate everything. So C should be run through monomials in E1, E. No, sorry, skip the bottom ones. You take n plus 1 divided by 4, round it up. Take that Pontryagin class, and then all the remaining ones in the Euler class, and say the total degree should be bigger than 2n. So don't take all of them, but take these ones. Miller, Maurice, and Mumford define for each of those a class in cohomology of this nonlinear Grassmannian. So using the cut code, we get this map. And Oscar and I prove that it's an isomorphism in that range of degrees. Roughly G over 2. 3 over 2 in this case. In the surface case, it's a little bit better, G over 1.5. That's what we can prove. So in the limit, let me just say that in the remaining limit. What we actually do, there's a similar diagram in the same way as you can increase the dimension of bundles, you can also increase the genus. So if you have a diffeomorphism, that's the identity near the boundary, you can glue in an extra copy of Sn cross Sn near the boundary. And you can keep going. And what we actually prove is that in the limit, so that would be the inverse limit in cohomology. That you get precisely in all degrees this free graded commutative algebra on the Miller, Maurice, and Mumford classes. Okay.
So this is all an assertion about the cohomology with rational coefficients.
Yep.
What about the torsion? Do you know anything about it?
Yes. So the nature of this formula is, so I know something about it. The formula is kind of homotopy. Theoretic, maybe I'll just tell you what it is in this case. So, that's an n-connected cover. Characterized by this space having no homotopy groups up to pi n, and this map being an isomorphism pi n plus 1 and higher. Maybe I don't want this thing, maybe I want the finite Grassmannian. N. formula looks something like you take the Thom space of the n-dimensional bundle, so the perpendicular complement to the canonical bundle here. Pull it back. Take the Thom space. Take the 2n plus capital N fold loop space, and then take the direct limit. N goes to infinity. This canonical loop space. And what we actually, the thing I wrote this way, what we actually prove is that that there's a map from one, which in this range of degrees is an isomorphism in integral homology, and therefore with any coefficient. So that translates the question to something that's independent of genus and so on, namely calculate the cohomology of this so-called infinite loop space. And that's a fairly standard exercise if you ask rationally. Oscar and I also wrote a paper about H1, so that's our torsion group. It's quite an interesting answer, but for H1 you can do it no matter what little n is, but the answer is like some summand of the stable homotopy groups of spheres plus an extra group that has the most core elements. And we also say what the extra thing is, but it's sort of a similar level of difficulty as stable homotopy groups of spheres. In the surface case, that was my PhD thesis, working out what the homology is with FP coefficients.
What is known about the case of four dimensions?
So half the story goes through, and there's nothing special about dimension 4. Namely, so they kind of, well, we proved two things. One is that if you increase G, then we prove that it induces an isomorphism into homology. When the degree is small compared to G. And the second thing we do is to prove that in the limit it integrally has the same homology as that infinite loop space. The second part goes through just as fine in 4 dimensions. So if you take the limit and then ask what the cohomology is, the answer is precisely this. But we don't know that the limit is kind of attained at any finite stage. So our theorem does not say anything about any particular genus, but if you phrase it as something about the limit, then it's the same answer. If you ask what fails, is because we use the Whitney trick.
Is the essential point here just that this WG1 is n-1 connected, or I mean, what's the special property of this family?
Right. Yeah, kind of. So, well, there's several sides to that bit, but Sn crosses n definitely plays a very important role in this story. So our theorem also, you could put something other than a disk here. You could put some other manifold with or without boundary. And in some sense, if you have a boundary, you can ask all the same questions. You could connect something with Sn crosses n and take the limit where G goes to infinity, at least if you have non-empty boundary. And we have a formula, it's a similar nature, but you have to put some other space here instead of this n connected cover. But that's the formula otherwise looks similar. Also, if you put a manifold that's not highly connected. So in that sense, it's not important, but yeah, I don't know what else to say. The reason that I took an n-connected cover here is precisely because that manifold is highly connected. So yeah, that would be. Another thing you could ask is what happens if you like connect some of this with an exotic sphere or something, and then you get the same answer, literally the same answer.
So in particular, I mean, naively one might expect that the diffeomorphism group of the boundary sphere would play some role. But the point is you're looking at things that extend across, and therefore you don't see the other connection components.
Yeah.
Further questions?
Come again?